Okay, so picking up part 3 of the 4-3 notes here. This is actually a pretty nice summary of dot product. So again, we saw on the last page of the last part of the notes here, the dot product. So again, what it said was the dot product between two vectors. So if I have a vector A, dot product of vector B, then the dot product between those is the magnitude of A times the magnitude of B, and then times the cosine of the angle between it. Like I said, this diagram is actually a very nice summary because it kind of breaks it down for different scenarios, right? So this is saying, what if the two vectors are going the same direction? Well, if they're going the same direction to where the angle between them is 0, then the dot product would be, again, the magnitude of A times the magnitude of B times cosine of 0. But we know cosine of 0 is really just 1, right? So the dot product between these two would just be the magnitude of A times the magnitude of B, which kind of, again, hopefully makes sense, right? In terms of vector multiplication, that maybe is about what we would expect for multiplying two vectors if they're the same direction, right? So why is this then saying that the dot product of A times B is greater than 0? Well, the significance here is if the angle is less than 90. So if I'm doing A dot B, if I'm doing the dot product of A and B, then I've got the magnitude of A times B times cosine of some angle that is between 0 and 90, right? So this angle is somewhere between 0 and 90. And what do we know about the cosine values between 0 and 90? Well, if you think about that part of the unit circle, right, isn't this the positive x-axis over here? Right, here's my x and my y-axis. So the cosine from 0 to 90 would always be a positive number, wouldn't it? So as long as the angle is less than 90 degrees, this product, this dot product, is always going to be a positive number, right? That's just a general kind of rule of thumb. What if it's exactly 90? Well, the cosine of 90, right? So if I look at this equation, it's the magnitude of A times magnitude of B times cosine of 90 degrees, but we know cosine of 90 degrees is 0, so then obviously the whole dot product would be 0. This is perhaps the most important conclusion because, once again, what does this tell us? Well, it says the same thing we already know about work, right? If work is the dot product between force and displacement, then what happens if force and displacement are perpendicular? So if the force is this way and the displacement is that way. Well, conceptually, we've already talked about it. We know that the work done should be 0. In terms of the dot product, it supports that conclusion, right? The dot product says that it would be force times displacement times cosine of 90, and cosine of 90 is 0, so that whole thing is 0. So the nice part about this, again, is it's consistent, right? The dot product is a method completely consistent with what we're already comfortable with for finding the work, right? So again, it's reiterating that work equals force times displacement times the cosine of the angle between them. And these go on to say, right, if the angle is greater than 90, if it's greater than 90, well, cosine of an angle that's between 90 and 180 would be a negative number, right? So it would be negative. And then finally, if it's exactly 180, then the cosine of 180 is negative 1, which is why this ends up being negative A times B. So anyway, nothing too tricky on that one, hopefully, but a very nice page here for summarizing the dot product. Okay, so I told you in the last part, we actually have another method we can work with for the dot product. And that's the reason that we go into this. That's the reason it's important. Because otherwise, it's the exact same thing we've already done, right? We can find the dot product by using the vector components. So what if instead of me giving you that this force was 20 newtons and that this displacement was 5 meters, right? What if I asked you to find the work, but instead of the vectors, I gave you the components? Is there another method we can do? Well, the answer there is yes, right? What we're going to do is we're going to basically distribute the components with one another. So I'm going to do the dot product of AX times BX. I'm going to do the dot product of AX times BY, dot product of AY times BX, and then the dot product of AY times BY. So I'm basically distributing, I'm foiling this outright. I hate that term, by the way, FOIL, because it only works with 2x2s, but we're distributing this function out. But anyway, so AX, and then I am keeping the I in here because that's telling me it's a horizontal component, right? Keep in mind, I is just saying it's a vector that goes off 1, 0, so it goes off in the positive x direction. J is telling me it's a vector of 0, 1, and so it's going off in the vertical direction, right? So that's all those subscripts are saying, but I am going to keep those in here, and I think you guys will see why in just a moment. But anyway, let's go ahead and carry out then that distribution, right? So AXI and then times BXI, so dot product BXI, and then AXI dot product BYJ, okay, so plus AXI dot product BYJ, Right, so I've distributed my first term, now I distribute my second one, so plus ayj dot product bxi, so ayj dot product bxy, or bxi, excuse me, and then finally plus ayj and then byj. Right, so ayj dot product byj. Obviously I know the subscripts here, all the variables kind of make it sound confusing, but if you take one step at a time, it's not too bad to distribute this out right. But anyway, the reason that's important is because now if I think about my dot product rules, well, the dot product says that if two vectors are the same direction, right? If two vectors are the same direction, then it's simply the magnitude of A times the magnitude of B. So if I think about this, that's where the I and J are very important. Because if both of these are I's, if they're both I's, aren't they both going the same direction? They're both going off in this direction, the positive horizontal direction, right? So if these are both vectors that are going off in the I direction, they are the exact same direction. So this whole part right here just becomes AX times BX. It just becomes the magnitude of those two values. So it's just the magnitude of this times the magnitude of this. On the other hand, if I have an I times a J, aren't those perpendicular, right? The I is going off in the horizontal direction, the J is going off in the vertical direction. And what do we know about the dot product of two perpendicular vectors? Well, we know, going back to this last slide, right, that if the vectors are perpendicular, the dot product needs to be 0, because the angle between them would be 90 degrees, and cosine of 90 is 0. So taking that here, that tells me that this whole portion right here, I don't care what AX and BY are, because those two dot products, those two vectors, I should say, are perpendicular, therefore the dot product is 0. Same type of idea with this one, right? J and I, once again, they're perpendicular, that whole thing is 0. So those two middle terms I got from my FOIL pattern ended up just being 0. So then when I look at my last term, well, these two are going the same direction, right? J's are both going upward. So this would be AY times BY. So this whole thing boils down to, even though it looks very complicated at first, this whole thing actually boils down to, if I have the dot product of A times B, so if I have vector A times B, then it actually is just AX times BX. It's the horizontal components multiplied plus AY times BY, the vertical components multiplied. So in simple, I'll give you a quick example here, and then we'll do a few examples that are actually in here, right? But if I give you the vector 2, 5, and then I give you, so if that's my vector A, and then I give you another vector that's maybe -3, 4. If I ask you to find the dot product between those, you just do x times x plus y times y. So 2 times -3, which is -6, plus 5 times 4, which is 20. So then the dot product would be 14, right? So that tells me the resultant, the dot product between those would just be 14. So this whole thing, even though I know it looks very complicated, actually works out very nicely, right? All we do is take the x components and multiply them, and then add that to the vertical components. So anyway, we'll see an example or two of that. But this is the context of the dot product that I do want you guys to get familiar with. Okay, so you should have seen this in pre-calc. You probably saw this at least a little bit. However, it's been a while since you've used dot products, so it's always a good idea to go back and review it. But let's look at this example, and hopefully you guys will see that. I know even though it looks complex, it's actually a very easy process, right? So if they ask me to compute the dot product, well, if I've got 3i plus 3j, and then b is 4i minus 1j, right? Again, it's just taking my x components and multiplying them together, and then taking my y components, multiplying them together, and then adding it up. So the dot product of vector A times vector B simply equals 3 times 4, the two x components, plus 3 times -1, and then obviously just combining like terms, or actually just calculating this and seeing what we get. So 12 minus 3, which is 9. So my end result is just 9, so the dot product is 9. Well, what's the significance of this? The significance is, if instead of A and B, what if I said that this was the force and this was the displacement? So what if this vector was representing the force and this vector was representing the displacement? Then the dot product of the force times the displacement, we just said it would be equal to 9, and we know the dot product of the force and the displacement is really the work. So what this just told me then is this is 9 joules of work, right, that I can do very easily without having to worry about magnitudes and angles and all that fun stuff. Right, so if they give us the components, then we just use the dot product this way, and it's a very quick and easy way to find the work done if they give me the force and the displacement. Okay, so then the last example I threw in here, kind of another side note, right? This isn't related to dot products, just another one I threw in to make sure you guys are okay with. So you've got a 70 kilogram skier gliding at 2 meters per second when he starts down a slippery slope. So he's up here at the top of the hill. He's already going, so he does have an initial velocity of 2.0 meters per second, and then it's a 50-meter long slope. What is with a 10-degree incline? What is his speed at the bottom? So I don't know that I necessarily need to work this one all the way out. The only reason I did throw this one back in here is I know every once in a while we tend to oversimplify these too much. If we want to find his speed at the bottom, we know that at the bottom he would just have kinetic energy because the potential energy down here would be 0, right, if we define that height as 0. The one thing you do have to watch out for is this one we do not just do potential energy equals kinetic energy, because at the top of the hill he's also moving, right? So the only difference between this and the other problems you guys have seen, we've got the potential energy plus the original kinetic energy, right? So the potential energy and kinetic energy at the top of the hill would equal the final kinetic energy he has at the bottom of the hill. So nothing too tricky on that one, right? Just set this up. So I don't know that I'll even bother solving this the rest of the way out because I think you guys can do it. But anyway, just find the final velocity, and then that finishes this example page. So the fourth example page I will actually probably just give to you guys, and then I may give you a key of it, but most of it will be review questions, so I don't think you will need a video necessarily to work through it. However, if you do have any questions on the fourth example page, just let me know, and I'm happy to help you guys with that too.